So we'll do problem 287. So if you have your book, a nice diagram there, but I'll try to get it all up here pretty quickly. We have an 8-foot long gate. So it's 6 feet long by 4 feet into the page with a weight of 800 pounds. And there's a cable up here that holds it like that. And for the current setup, the angle is 60 degrees. Obviously, if the cable gets in more tension, that angle will change. But for this configuration right now, the question is, what is the tension in the cable? All right, so recall that we had, let's see, if I'm not mistaken, we defined our H to be, I forget, where did we find H and Y? You guys have been studying more than I have. Y is angled or H is? Y is angled. I'm going to trust you. Okay, well, I have to tell you, that's not what I'm seeing in my notes, so they might have just been inconsistent, which is not beyond them. Let me just see how I presented it. YC is angled. H goes straight down. Oh, no. Okay, got it. Okay, we're good. Okay, so recall that we had our Y is in this direction, and our H is defined this way. And what we are looking for is the, the center location. We want to get the pressure at this point because there's a pressure distribution on here that goes from 0 up to maximum, just like the drag you guys determined the drag on that equilateral triangle in your homework problem. It's going to have a very similar look to that, where the pressure always acts normal to the gate. So maybe better to even step back just a tiny bit here and draw our free body diagram, which will then relate the unknown to things that we'll then have to determine about our system, and therefore will become known quantities. At our hinge here, it's a hinge, so we have, let's just call this H for our hinge. This is our HY. Wow, that's confusing. Y, huh? Here's our H in the vertical, I'm just going to call it. This is our H in the X direction. I think we can use that. But regardless, those aren't going to matter, right? Because how do we relate all these quantities? Well, some moments about our hinge. We know we have tension up here at the top, at the 8 feet away from our hinge. And here's where our water lives. Oh, we have weight. And then our pressure is going to act, the resultant due to pressure is going to always be normal to the gate. And that's a resultant force due to our hydrostatic pressure. So we know that let's get another diagram where we can just talk about that hydrostatic pressure force. If this is the water level, this is our ground, we know that the location of the resultant is going to be, halfway along the gate here, right? And so, but then we also have the resultant force we know from our equations is the pressure at that center point. So that's gamma, the H of the centroid times the cross-sectional area of the gate. Right, so we can take this pressure prism and condense it down into the average pressure quantity, and then apply that average quantity over the entire gate. Yeah.
So why is it halfway?
Okay, I should be careful. The magnitude of the force, you take the average pressure value, which is at HC. Its location, so for the moment arm, is going to be 2/3 down. And that's what we call the center of pressure. It's not at the centroid, but you take the centroid value to get you your average pressure. So you take, in the formula for the magnitude of the hydrostatic force, you use the centroid location to get your average pressure for the triangle. And then it actually acts, its moment arm is 2/3 down. Yeah. And now you're talking about the centroid of the actual triangle, whereas the HC, we're actually taking the average quantity of the triangle, where the other one is the centroid of the area that it makes up, that the prism makes up. Okay, so right now let's just deal with the magnitude. We know that this is going to be, we know gamma and A, the area, but we need to know what the HC quantity is. So here's our YC, HC is there, and where's our angle? That lives, there's our angle, so that means that this angle, right? You guys agree? Yeah. So HC is just going to be YC. We know YC is just going to be the 3 feet, or the 6 feet over 2, and then we just hit it by sine. Is sine the nice one at 60 degrees? Sine is the not so nice one. That's the nice one, right? Sine of 60 degrees is just a half. You guys agree? No, it's root 3 over 2. Oh yeah, because it's a y value, yeah. Okay, so we'll just leave it as sine of that, but it's root 3 over 2. I thought maybe we could get away with just plugging this as 6 over 4 or 3 halves, but nope. Okay, now to then find, so at that point we now have all the information to determine the resultant force. In general, the location, this is what we said, was the moment of inertia over this guy, and then we have, using the parallel axis theorem here. We know that our YC is that 3 feet that we used up here. Right, this really is YC. And our moment of inertia, this is just a square. 112 bh cubed. So now this is the, we're trying to find the moment of inertia about the x-axis as the pressure sees it. All right, so in that normal direction. So it's just a rectangle of 6 by 4. And the moment of inertia about that x-axis is just 112 bh cubed. So if you plug all this in, you get, well, I don't know what that is, but whatever this guy is, plug all the numbers in. We know that this is 3 feet. This turns out to, I guess, be 1 foot. And this is 4 feet. So that's running through the technical side of it. But as you can see, that puts you 2/3 of the way down. And that's what's going to happen as long as, your pressure prism starts at the free surface. It'll always be 2/3 of the way down. You need to go through this more carefully if your pressure prism doesn't start at the free surface, and you have that, like the Homer problem that you guys had, where there's some like underground bunker that's pressurized, and the gate of interest starts, below the surface or whatever. Does that make sense? This worked out. You just go 2/3 of the way down, but that only works if your pressure prism starts at 0. The pressure represents the weight of the water above it. This force here, the resultant force, is representative of the weight of the water above it. That was your question, like just in general about the free body diagram and how we set it up. This is the issue of already knowing the exam, but benefit to you guys. This is probably the most complicated moment of inertia you'll see on the exam. I will not provide any table of moments of inertia. The moment of inertia of a rectangle is 1/12 bh cubed, and I guess that's understood that we are comfortable with that. Yeah, after statics, dynamics, and mechanics of materials, I guess. No? You don't think so? 1/12 bh cubed. All right. Here's the deal. With stuff like that, if it comes up, I would probably be more than willing to give it to you. However, not everyone is here in the exam setting. So those of you, and I see all of you are here today, you do need to know 1/12 bh cubed. But yeah, I wasn't planning to give it. But like I'm saying, if something else like that comes up, I try to avoid things. But if it doesn't show up on the exam, it is kind of expected that you knew it. But I don't want that to be the reason you're missing points or whatever. Basically, anytime I have to put another page, there's another 120 pages stripped away from a tree, right? So I'm trying to reduce all the tables. You can imagine with drag coefficients, friction factors, I've been able to fit all of the appendices onto one page, and I don't want to put anything more. But, okay. Huh? Yeah. I'm stalling here because I just thought of something, and I don't remember it. Okay. Okay, the statement I want to make also is that another reason for not giving you tables like that is because then it would then assume that you need to use it. By not giving it to you, it's a sign that if you're looking to calculate a moment of inertia, perhaps you don't need to use it. Try to find a better way to answer the problem. Okay? Maybe that'll become relevant in a day from now, but yeah. I just was in my head like, oh, should I put it on there? But no, that would then trick. I think it would be a way to, it would lead more to a tricky whatever result. Okay, let's wrap up this problem. I want to get to fluids that move. All right, so our equilibrium, I think we're now set up to get our equilibrium. That is sum of the moments about h must be 0, as long as the cable isn't breaking. All right, so what do we have here? Well, this is the moment about let's start at the top and work our way down. Tension is what sine of cosine? Yep, cosine times it's 8 feet. You guys agree with that? Hmm? Yeah, why? I mean, who? You guys now, both of you, I've heard cosine and sine. What is it? This is a long day for you. Huh? Theta is 60. Oh, yeah, that's it. That's it. You're right. You're right. So then this is 90 degrees minus. So that's right. That's why. Okay. So we're picking up that guy. There's another, right. So the way I was trying to do it was just getting the component of the actual force itself that's in that direction. But we need a sign in this case. Let's see, our weight moving down, the weight is going to live at 4 feet, and the distance here is from the line of action is that one's cosine. All right. Our resultant force doesn't need to be hit with any sign. That's also minus. And we already found YR. And that's it. This equals 0. You can solve for tension. Everything else is known. We know YR. And W is given as 800 pounds. Good call. Two feet. That's why you guys are here. Otherwise, I just do this on my own, and I get a lot of mistakes. So. Okay. So what do we have now? Let's see. We could do control volume system. We could do something with potential flow or viscous flow or pipe or external flow. Let's limit it first. Do you want to see control volume, differential analysis? That's one option. Or pipe flow, external flow. All right, I'll just choose. I'll tell you that these could be test problems. You guys don't know that. Right? So